My dear friends, welcome to Rajashekhar classes on Applied Data Science with Python. This is lecture number 363. In this lecture, I will continue my discussion on gradient descent algorithm and its geometric intuition. Let's consider this particular graph. This is y equal to f of x. What is my step number 1? Pick an initial point x0 at random. Pick any point. It could be any point on x-axis. Let me choose this one as my initial point. Yes, just check this one. This one is my initial point. What is step number 1? In gradient descent algorithm geometric intuition, step number 1 is pick an initial point x0 at random. We want to find x1, isn't it? Yes. We have x0. We want to find x1. Yes, this is step number 1. Pick an initial point x0 at random. Step number 2, we want to find x1 such that x1 is closer to x star. This is x star. This is x star is this one. This is the solution, isn't it? Your x1 must be, we want to find x1 such that x1 is closer to x star. What is this x star? This is optimal. I can say this is optimal x, isn't it? Yes, optimal x star, the optimal x. So you want to pick your x1. Where will you pick your x1? Somewhere in between x star and x0, isn't it? Somewhere in the region between x star and x0. How do you pick? It is very simple rule of the gradient descent. What is that rule? That rule says x1 equal to x0 minus r into df by dx at x0. What is this r? So what does it do? Let's see. This r is constant. R is, I can say, r is step size. R is often called as step size. This is a constant that you will fix. We will see what happens as step size changes. For right now, for simplicity, let's say the step size is constant. Let's take my step size as 1. Let me assume my step size, this value as 1. How to pick the right step size? It is very interesting area of research. Let's assume your step size is 1. Now what is df by dx at x0? Just we will try to understand what is df by dx. Anyway, we are saying about r is step size, and now we will try to understand what is this df by dx at x0, isn't it? Df by dx means what? What does it mean? It is slope, isn't it? What is df by dx? It is nothing. This is nothing but slope. This is df by dx at x0 is nothing but slope. This is, let me say, this is x0. What is the slope? You can find slope, isn't it? But this is not the slope of this line, isn't it? Now, what is the slope of this line? What is the slope? Slope is, what is the slope? Slope is positive, isn't it? We already discussed about slope in our previous lectures. Therefore, I can say x1 equal to, what will you get here? As slope is positive here, as slope is positive, this already we discussed in our previous lectures. We are fixing r as 1. We are assuming r as 1. df by dx at x0 is nothing but slope, which is positive quantity, which means you are subtracting from x0. You are subtracting this quantity from x0. You are subtracting positive value from x0. R is 1. Anyway, df by dx is positive at x0, isn't it? This slope is positive. df by dx is positive. R is 1. Therefore, you are subtracting a positive quantity from x0, isn't it? You are subtracting positive value from x0. When you do that, what happens? You have to move towards x star, isn't it? Just what we are doing, this is 1, this is positive quantity, some positive quantity is subtracted from x0, therefore you will move in this direction, isn't it? Therefore you are moving towards, I can say you are moving towards optimal solution. This x star is optimal solution. What does it mean? As you are subtracting some positive quantity from x0, I can say your x1 is less than, why? Because x1 equal to x0 minus, you are subtracting something from x0, then you are getting x1, means what does it mean? Your x1 is less than x0, because this value is positive. 1 into positive is positive value. You can pick x1 somewhere in between. Your x1 is in between, somewhere in between your optimal solution x star and x0. It is in between. It is as your x1 is moving towards x star optimal solution, you can find your x1 somewhere in between x star and x0. Notice that because your slope or your derivative at this point x0, what is the derivative or what is the slope at x equal to x0 is positive, and you are subtracting this with step size of 1, you are moving closer to x star. Your x1 is closer to x star than x0. Your x1 is closer to x star. This is x star. I can say, let me say x1 is somewhere here, as we are subtracting some positive quantity from x1. Therefore, x1 is closer to x star compared to x0. Now, just observe this graph carefully. Now, let's see other way around. Other way around means, let me consider this one. Just see. Now, let's see the other way around. Let's imagine what would have happened if my x0 on other side. Other side in the sense, let me assume this is my x0. This is my x0 is on the other side. Let's assume my initial point is here. This is my initial point x0, and this now I have to find the slope, isn't it? And what is the slope at x0? I can say, and this is the negative, isn't it? This slope here in this, if you find slope in this direction, what slope will you get? You will get negative slope, which we discussed, isn't it? Just see, this slope is negative. Here you will get negative slope, isn't it? We already know why it is negative. Now, what is our update is? Our update is x1 equal to x0 minus r into df by dx at x0. R is anyway we fix it to 1, and df by dx is slope at x0. Slope at x0 is negative, r is 1. 1 into negative quantity, negative into negative positive. Therefore, you are getting x1 equal to x0 plus some positive quantity you are getting, isn't it? What does it mean? Your x1 is bigger than x0, isn't it? I can say your x1 is somewhere in between. Where can I find? X1 is somewhere in between x0 and x star. This is optimal solution, isn't it? What is our update rule? x1 equal to x0 minus r into df by dx. Our df by dx at x0 is a negative value. That is important here. Df by dx at x0 is negative value, and we said r equal to 1. So what happens? Your x1 equal to x0 minus 1 into negative quantity, which means x1 is greater than x0. Therefore, x1 is moving. Your x1 is moving towards x star. Means your x1 is closer to x star compared to x0, isn't it? X1 is closer to x star. Just say your x1 is closer to x star. Whether I must say like this, x1 is closer to x1 is closer. X1 is closer to x star, isn't it? Than x star, than x0. Whether you pick the initial point, whether you pick the initial point on the whether you pick the initial point on the left side of x star or right side of x star, your x1 is always closer to x star, whether x1 is closer to x star than x naught, whether you pick the initial point on the left side of the minima, or this is minimum value, isn't it, or optimal value, whether you pick your x naught either left side of the minima or right side of the minima. In our second step, what we did in our second step, basically we got our x1, isn't it? We got our x1. Since we got our x1, let's draw the function again. Let me draw it. Anyway, we have a function, isn't it? How can I find x2? Now I have x1. How can I find x2? What is the formula for finding x2? x2 equal to x1 minus r into df by dx at x1. Again, this df by dx at x1, what is this? This is slope, isn't it? Again, slope here, it's at x1, this is x0, this is x1. Now I am finding slope at x1, isn't it? Slope here, what is slope at x1? It is a positive quantity. x2 is somewhere x2 is I am finding x2 is still closer to x star, isn't it? x2 is still closer to x star compared to x1. Similarly, at any iteration, what we do this, at any iteration, your xi plus 1 equal to xi minus r into df by dx at xi. This is the update, isn't it? This is, what is this? This is update function. This is update. This is simple, I can say this is simple iterative algorithm. Simple iterative algorithm. Using this, we start with x0. We started our journey with x0. From x0 you are getting x1, from x1 to x2, x2 to x3, so on xk, isn't it? Let's assume at some iteration, kth iteration, let me say we reached xk. Let me assume I reached xk. What is my xk? xk equal to xk minus r into df by dx at xk minus 1. Once we reached xk, now let's assume we computed xk plus 1 minus xk. Let's assume we computed xk plus 1. If xk plus 1 minus xk is very small, which means your xk is reached to optimal value. If your xk plus 1 minus xk is if it is very small, very close to x star, then terminate your loop and you can declare x star equal to xk, because you are updating from what happens. For example, from x0 to x1 there may be 0.5 difference, this may be some 0.4 difference. From xk plus 1 xk2 you may get some 0.00001, means there approximately your difference between xk plus 1 and xk is so small. In such case, xk is optimal value. This is how gradient descent works. Gradient descent is an iterative algorithm with simple update function. What is simple update function? Your xi plus 1 equal to xi minus r into df by dx at xi, isn't it? This is update function. Remember, if you have vector function, if f is a vector, let me assume if your f is a vector, what happens if f is a vector function? Then this df by dx is simply replaced by del f with respect to x at xi. Wherever your df by dx, you can, wherever this df by dx appears, you can replace it by del f with respect to x. Now, in the case of if your f is vector, that is important. If your f is vector, this df by dx can be replaced by del f with respect to x at which point, as it is xi plus 1, it is at xi. Now here one very interesting aspect that I want to cover. Let's draw a function. Just let me take this function again. Yes, this is function. Let's assume this is, what is my minima, what is my x star, this is my x star. This is my x star. This is my minima, isn't it? Let's assume this is my minima. This is my minima or optimal value, isn't it? At any iteration, xi equal to xi minus 1 r into df by dx at xi minus 1. Remember, as we are coming closer and closer to x star, this is x star, my slope is reducing. Here I can find slope, isn't it? Your df by dx at x naught is greater than or equal to df by dx at x1, isn't it? Which is greater than or equal to df by dx at x2. As we are coming closer and closer to x star, my slope is also reducing, and eventually our slope becomes 0. Here your slope is 0. That we already discussed in our previous lectures. It decreases, slope decreases, and slope becomes 0. So at every iteration, our slope is decreasing, which means df by dx at x naught is greater than or equal to df by dx at x1 is greater than or equal to df by dx at x2. So remember what is happening. Slope or gradient is slowly reducing. What happens in gradient descent? Initially from x0 to x1 we will make big jump. From x0 to x1 we will make big jump. Why? Because your df by dx value is bigger than df by dx value at x0 is your, for finding x1, what is the formula? x1 equal to x0 minus r into df by dx at xi minus 1 means what? This is x0. df by dx at x0 is bigger than df by dx at x1. Your jump from x0 to x1 is bigger than jump from x1 to x2. Initially, I can say, let me repeat. So remember, what's happening? Slope or the gradient is slowly reducing. What happens in gradient descent? Initially, from x0 to x1, we will make big jump. We will make big jump. We will make big jump from x0 to x1 because this df by dx at x1 is more as you closer and closer, and your slope is more than df by dx at x equal to x1, isn't it? Just see, this is a formula. Now you can understand. How can I say this one? Let me say df by dx. Yes, df by dx at x0. I can say df by dx at x0 is significantly more than df by dx at x1. We will make big jump. We will make big jump. We will make big jump from x0 to x1, isn't it? Our r is kept almost constant. Let us assume r is constant, which is equal to 1. Now just this jump is bigger. This jump is little bit smaller, isn't it? This is still smaller. This is still smaller. Something like that, isn't it? Just try to go through this lecture. If you have any difficulty, please keep a comment. In my next lecture, I will discuss about an important concept known as learning rate. Learning rate, or I can say step size. What is this learning rate or step size? We will try to understand in next lecture, that is in lecture number 364. Thank you very much.